Hello everyone, I'll be your host for the day, and today we'll be looking at doing calculus with parametrics and vectors. Before we start on going into these problems, there are some important concepts for you to understand. Let's start with learning the basics and operations of parameters. As you probably already know, a parametric involves a third variable, typically labeled as t for time. When you define the parametric, x and y are usually shown as functions of t. For example, let x equal 3t and y equal t squared, where 0 is less than or equal to t is less than or equal to 3. Conceptually, you can think of parametrics as tracing the position of a point while it moves around an xy plane. At any time t, you can determine the x and the y with the x and y functions, and the combination of all the places the point can go makes up the curve of the graph. In this specific parametric graph, 0, 0 would be the initial point, while 9, 9 is called the terminal point. In addition, we can use a technique you likely already know with parametrics, eliminating the parameter. We can solve for y in terms of x, and doing a quick substitution, we get y equals 1/9 x squared. Miraculous! With this, predicting the shape of the curve becomes trivial. However, notice that the parametric does two things our traditional rectangular system is unable to do. First of all, we are unable to find out the direction the point travels along the path of the line. In addition, we have no idea how quickly it moves. These problems will be discussed in the second part of this video, but for now just keep it in mind. Question number 1. Consider the following parametric equation. X equals ln 2t plus 15, and y equals 3 over t plus 2. Our first course of action will be to find what the slope of this function is at time t. Oh no, I hear you cry. There are two functions? Which one do we derive? Believe it or not, we'll have to do both. Leibniz's notation will come in handy when doing this. Remember, what we want is dy dx, the instantaneous change in y over the instantaneous change in x. Let's start by taking the derivative of x as a function of t. A quick chain rule gets us dx dt equals 2 over 2t plus 15. Doing the same for y gets us dy dt equals negative 3 times t to the negative second. Now here comes the tricky part. Clearly, dy dt and dx dt are only representing the rate of change for x and y over time separately. But what if we put dy dt over dx dt? Dividing the change in y over the change in x will in fact get us exactly the equation we need. So dy dx is equal to negative 3 times t to the negative second over 2 over 2t plus 15. Simplify that out, you get negative 6t plus 45 over 2t squared. And that's all there is to it. Thus we can calculate the slope of the graph at any time t. Note that here, dy dx is not how quickly the point moves, but simply the slope of the graph drawn by our parametric equation. After all, the speed would be something over dt, or change in time. But wait, if there's a first derivative, there's always a second. Time to do concavity. Let's start by thinking about how we tackle this problem when things are just in terms of x and y. Given a dy dx, the most easy and straightforward thing to do would to just ddx it, or take the derivative by x in order to find the second derivative. However, we have dy dx in terms of t. The solution may seem difficult, but actually if we look back, you may notice that the previous thing we did to get dy dx in the first place was solving the same dilemma. To explain, since ddx of y is equal to ddt of y over dx dt, it clearly follows that ddx of y prime is equal to ddt of y prime over dx dt, where y prime is simply substituting y with dy dx. With this, the question becomes easy. First find ddt of y prime. ddt of y prime is equal to ddt of negative 6t plus 45 over 2t squared. Simplify it out. You get 12t squared minus 180t over 4 to t to the fourth. Cancel out, 3t minus 45 over t cubed. Then do exactly what we did last time. Divide by the derivative of x relative to t. So ddt of y prime over dx dt is equal to, do the math, 3 times t minus 15 times 2t plus 15 over 2t cubed. And voila! Using this, we can tell the concavity of the graph formed by the parametric again at any time t. Whew, that was quite the parametrics workabout. Now on to something eerily similar, but not quite the same. Vectors, quantities with magnitude and direction. First off, let's check out the two-dimensional standard notation. A vector usually looks something like this. S of t is equal to f of t comma g of t, or f of t I plus g of t j, where f of t is the function representing the x value at time t, and g of t is the function representing the y value. To illustrate, here's a really easy example. S of t is equal to 3t comma t squared. Say what? What do you mean I've done this before? You mean to say this example is exactly the same one we started this video off with? It clearly isn't. We're doing vector graphs now, not parametrics. Fine, I'll admit it. The two examples are basically the same, but with a few key differences. First of all, I'm sure you've noticed that I have not bothered to place bounds on t. That practice is mostly a quirk of parametric graphing. However, there is something else about vectors that are special. Here's maybe if I draw a few, we might begin to see some implications. Take a look at the vector for this graph at t equals 1. Each vector has an x component and a y component. While you could represent in a way similar to coordinate points 3, 1, writing it as 3i plus 1j shows its nature as a vector. Here I and j are not numbers. I represents going a single unit right, and j represents going a single unit up. Hence the combination of going 3 units right and 1 unit up becomes the unique vector we see here. But that's enough small talk. Let's come back to the realm of calculus. What would it mean if I told you to take the derivative to t of the vector equation s of t? Doing the calculation is actually ridiculously simple. Just take ddt of each component of the vector function. Hence s prime of t, or v of t, is equal to 3, 2t, or in general, s prime of t equals v of t equals f prime of t, g prime of t. That's odd, I hear you say. Why did you rename it v of t? Elementary, my dear listener, for as you can see, taking the derivative of the x component followed by the derivative of the y component gets you the velocity. Unconvinced? Why don't we graph v of t first? Looks like it's just a vertical line. But I say, a vertical line with meaning. Let's compare. At t equals 0, the velocity of the point on the graph of s should look something like this. At t equals 1, it will look something like that, and so too at t equals 2. But imagine what happens when we drag the velocity vectors from our first graph and line them up the second so that the tails of each vector are all at the origin. Incredible! The velocity vector function acts as the derivative of s of t in a very special way, by showing not its slope, but the direction it is going in. Perhaps now is the time to leap into a new problem. Question number 2. Given that the velocity at time t is equal to v of t is equal to e to the 3t minus 4, 2t cubed, sine of t, find s of t such that s of 0 is equal to negative 4, 3, ln 2. Right off the bat, you'll notice that there are now not 1, not 2, but 3 dimensions. Not to fret, for little has changed. Taking the derivative is merely the work of doing ddt of the first, second, and third component. Yet taking the derivative of velocity might not be so wise to do here. You'd get the acceleration instead of the position function. Instead, we can integrate it. Understanding that integrating a whole vector is essentially the process of dissecting it by integrating each individual function is the key to solving this problem. So we get s of t is equal to 1/3 e to the 3t minus 4 plus c, 1/2 t to the 4th plus c, and negative cos t plus c. Notice in the same way that 3 c's may represent 3 different words in an abbreviation for chocolate chip cookies, these 3 c's are individual and different as well. To solve for each, we can use the initial condition given to us in the question statement. So 1/3 of e to the 0 plus c is equal to negative 4, c is equal to negative 13 over 3, 1/2 of 0 plus c equals 4, c equals 4, negative cosine of 0 plus c equals ln 2, c equals ln 2 plus 1. With the c constants found, we can finally come to the solution. S of t equals 1/3 e to the 3t minus 4 minus 13 over 3, 1/2 t to the 4th plus 4, and negative cosine t plus ln 2 plus 1. Whew, man, vectors are quite the subject, aren't they? Okay, one last topic before closing off for the day. Speed. Back in ye olden days, we represented velocity as just a positive or negative number, indicating going forwards or backwards respectively. Thus, getting the speed, i.e. the magnitude of the velocity, was just a matter of taking the absolute value. However, everyone knows we don't live in a single-dimensional number line. So what is speed in 2D? Well, consider a velocity vector, like this one, again with an x component and a y component. Logically, the speed is just the length of the vector. My dear friend Pythagoras has already solved this problem 1,000 times over. Just take the square root of x squared and y squared, and you'll have gotten the magnitude of the vector. So in general, the speed in 2D would be the square root of x squared plus y squared. In 3D, x squared plus y squared plus z squared. And in 1D is the square root of x squared, which is exactly what absolute value of x is. Oh my god, we are seriously breaking new grounds here. But wait! What happens if you take the integral of speed over time, from let's say some time alpha to some other time beta? Everyone knows the integral of speed is distance, and the distance traveled following the curve. Oh my god, it's the arc length! Again, strokes of genius. So we can state that the arc length of a given vector equation is L equals the integral from alpha to beta of the square root dx dt squared plus dy dt squared dt. To clarify, we write dx dt and dy dt instead of x and y because we're looking at the x and y components of velocity, not position, and the derivative of the position x gets us the velocity x, so yeah, pretty incredible. Not only does this extend to 3D arc lengths, as long as you add an additional dz dt squared term, but it also applies to parametrics. After all, in both cases, the square root of change in x squared and change in y squared gets you how quickly something is traveling. And what better way to find distance traveled than to take the integral of speed, am I right? And there we have it, calculus with parametrics and vectors, and how to solve them. Hopefully with that, you feel at least a little enlightened in the subject. That's all for now. Thanks for tuning in.